Okay, so as promised, we're going to do some practice problems before we move on to the last part of equilibrium. Ready? Let's do this. So pause me, do this problem, unpause me, and then we're going to go over it together. In this problem, I give you an equilibrium equation, and what I ask you for, I actually don't ask you for the equilibrium concentration. I give you that. I ask you for equilibrium constant. You need to figure out the K. What is K? Okay, this is a little bit new. We haven't done a problem like this. Now, the first thing that I like to do, especially when I don't know where to go with a problem, I like to put ice table. Yeah, we like ice table. Put up the ice table, put things in, fill it up, and then that gives you a direction to go. So initial, change, and equilibrium. Okay, so initially you have 5 moles of O2 and 4 moles of NO that are mixed together. Do you agree? And then, this is very key. It says that this is a 1 liter solution, so all the moles will be the same thing as molarity, because to plug in to the ice table, you need molarity. To plug into the ice table, you need molarity. Okay, but again, it's because it's 1 liter solution, moles over 1 liter, these would be the same, the moles would be the same as molarity. So, NO is 4.0 molar, O2 is 5.0 molar, and I don't have any of the product at the beginning, right? Okay. Now, because I only have the reactant and I do not have the product, that means the change has to be reactant going away, disappearing, and product forming. You follow me? So because I have nothing but the reactant at the beginning and I have 0 product, the change is going to be the reactant going away, disappearing, and the product forming. So this would be minus 2x minus x plus 2x. And we said the coefficients matter because this is a mole ratio. For every 2 moles of NO that disappears, 2 moles of NO2 form. For every moles of O2 that disappears, 2 moles of NO2 forms. Mole ratio, we've done this, we got this down. So of course those also matter here. So at equilibrium, it will be 4.0 minus 2x, whatever that is, and then 5.0 minus x, and then 2x. So the x tells us basically how much is going to disappear and how much is going to be formed. All right. Now we have this. So far so good. Now here's the thing. We don't have k to figure out x, right? We don't have k. We're trying to figure out k so if k was given, I could figure out what x is. But k is not given. I'm trying to figure out k. But what else is given to me? They tell me the concentration of NO2 at equilibrium. That's interesting, isn't it? They give me at equilibrium, the concentration of NO2 is 1.5 molar. How could I use that? So at equilibrium, the concentration of NO2 is 1.5 molar. Again, it's a 1 liter solution. So 1.5 moles divided by 1 liter, it would be 1.5 molarity, right? Molar. Because you have to have molarity to plug into this. To plug it into the K equilibrium is concentration of product over reactant. So molarity is what we want. We have moles, but again, it's 1 liter solution. So the moles will be the same thing as molarity. All right. So at equilibrium, the molarity of NO2 is 1.5. Okay, so that means right here, this is 1.5. At equilibrium, the molarity of NO2 is 1.5. That means 2x is, what did I do that for? That means 2x is 1.5. That means 2x is 1.5. So what is going to be x? X is going to be 0.75. 0.75 molar. You guys follow that? Okay. I'm going to go over it one more time to make sure you got this down. So what we did, we saw an equilibrium, we saw an equilibrium equation, and what we did, we put ice table. Ice table is good. Initial, these are the initial concentration. I have no product at the beginning, and then the change would have to be the reactant disappearing and the product forming. Don't forget the mole ratio, that matters. And then at equilibrium, this is my formula. I don't have K. If I had K, I could just figure out X, but I don't have K. But what they tell me at equilibrium, this is the equilibrium, at equilibrium, the NO2 concentration is 1.5 molar. I know at equilibrium, NO2, it has to be 2X, right? So NO2 has to be 2X at equilibrium, so I can figure out that X is 0.75. Yeah? Okay. Now, the question asks you for equilibrium constant, right? The question asks you for equilibrium constant. And now what the piece of information we have the X. So, let's go to the next page. What is going to be my equilibrium constant? It's going to be concentration of NO2 to the power of 2 over concentration of NO to the power of 2 times concentration of O2 to the power of 1. So now what I have to do, I have to figure out all these concentration and plug it in to get K equilibrium. Now, let's do this. So, NO2, we know that concentration at equilibrium is 1.5 molar. That was given, right? And also, we figured out X, and X was 0.75. So, the next thing we need to do, we need to figure out the concentration of NO. How do we do that? Check this out. Okay, I'm going to go back to the last page. We know X is 0.75. So, for NO concentration at equilibrium, it would be 4.0 minus 2 times 0.75. I'm going to say one more time. So here are the formulas for at equilibrium. We know X is 0.75. All I have to do is plug in 0.75 for X to figure out the concentration of NO at equilibrium. Alright, so if we haven't lost anyone, so that would be 4.0 minus 2 times 0.75, and I get 2.5 molar. I'm going to do the same thing for O2 concentration. If we come back over here, the O2 is what? 5.0 minus X would be 5.0 minus 0.75. 5.0 minus 0.75. I get 4.25 molar. These are all the concentration at molarity. So all I have to do is plug it in, right? All I have to do is plug it in. Again, one more time. These are the concentration at equilibrium. At equilibrium, these are the concentration. If I plug them all back in here, I can solve for equilibrium constant. Let's do it. So NO2 is 1.5 to the power of 2 over NO is 2.5 to the power of 2 times O2 is 4.25 to the power of 1. Now I'm anticipating what kind of question you have right now. So remember, these are the concentration, right? These are the concentration. But the formula calls for concentration over the stoichiometric mole ratio. So you still have to do that because 105 is concentration. Basically, the 105 is this one right here. So you can plug this one in, but you still have to square it. The same as here. 2.5 is the concentration over here, but it's still you have to square it. Yeah? Okay. So, what am I going to get? If I plug everything in, what I get is 0.085. That is going to be my K equilibrium. That is going to be my K equilibrium. Not bad, yeah? Yeah, we hadn't done a problem like this. That I give you the concentration, ask you for K equilibrium. All right, ready for the next one? Let's do it. Next one is, okay. Again, do this problem, pause me, do it, unpause me, we're going to go over it together. So you charge a 1.6 liter flask with 26.4 grams of NO2 at 200 K to study the following reaction. So this is our reaction. Our reaction is equilibrium. You have a forward and a backward reaction. After allowing the system to reach equilibrium, there are 0.12 moles of O2 in the flask. What is the value of Kc in this reaction? Okay. I'm sure you can do this problem, especially we did one very similar to it. Now I'm going to write down the equation. The equation was 2NO2 going back and forth to 2NO plus O2. Okay. Now, is asking you for K, is asking you for equilibrium constant. Well, you know how to do that, don't you? Right? Is asking you for equilibrium constant. So what we're going to do, we're going to do an ice table, right? We're always going to do an ice table. So hopefully that's what you did. You go, okay, they're asking for equilibrium constant, equilibrium equation. Maybe I don't know where to go, but I want to put the ice table down. Then I know where to go. So initial, change, and at equilibrium. So at the beginning, what do you have? You have 1.6 liter flask with 26.4 grams of NO2. Okay, so that's what you have at the beginning. You have some NO2. But again, remember what you need. What you need to put in here, you need to put in here molarity. Molarity is not given to you. That's the interesting part of this problem. Molarity is not given to you. But can you figure out molarity? Sure. So what they give you 26.4 grams of NO2. I can convert that to molarity because I can convert grams to moles, right? Using molecular weight, I know how to do that. 1 mole of NO2 is 46 grams. I know how to do that. So if I do this, again, grams get cancelled out. I get 0.574 moles of NO2. Now, this question says that is 1.6 liters. So now what I have to do, I can just divide that. I can divide this by 1.6 liter. Now I have moles over liter, and that will give me molarity, which is 0.359 molar. So that will be molarity. So they don't give me molarity. They give me grams, they give me volume. Hey, I know how to do that. Gram to moles. Moles divided by volume gives me molarity. So the initial, this is the initial. I means initial. This is the initial molarity. What I have at the beginning, I have 0.359 molar of NO2. Now, do I have any of the product? I don't have any of the product. Okay? All right, this is kind of the same as before. So I don't have any product, but I have reactant. Every time that's the case, remember, this has to be minus because this has to go away, and then the other one has to form. Because I don't have any product, I only have reactant. So the only option this has is moving this way, right? Now again, the stoichiometric mole ratio matters. You know that. So the change would be -2 plus 2nx. So at equilibrium, I would have 0.359 minus 2x, and I would have x. You guys following me so far? Okay. Now they're asking me for Kc value, right? For the K equilibrium. So if I had been given K equilibrium, I could solve for x. But I'm not given K equilibrium. I want K equilibrium, so x has to somehow be given to me. Now, is x somehow given to me? Yeah. They said after allowing the system to reach equilibrium. So when it's in equilibrium, after it reaches equilibrium, there are 1.2 moles of O2. Okay, so after it reaches equilibrium, so at equilibrium, in equilibrium, we have 0.12 moles of O2. Again, I need concentration. K equilibrium is concentration of the product over concentration of reactant. I need you to write that down somewhere in your lab notebook. Your lecture notebook, that you need concentration. So I can find concentration. So at equilibrium, what I have 0.12 moles of O2 over 1.6 liter, because that is the volume of our flask. So if I do this, what I end up getting is 0.075 molar. 0.075 molar. That is the molarity of that at equilibrium. Now, what does that represent? What does this represent? So here is the molarity of O2 at equilibrium. So if I come over here, pay attention to this. If I come over here, this is O2. At equilibrium, O2 is X, right? At equilibrium, O2 is X. And I know at equilibrium, O2 is 0.075. So what is my X? My X is 0.075 molar. I'm going to go over one more time just to make me feel better if I do it. So at equilibrium, I know this is the concentration of O2. When I come over here, at equilibrium, O2 is just X. So 0.075 is going to be my X. Now what do I do? Okay. Now I want to write the equilibrium constant and try to plug everything in, right? Now before I do that, so I know that O2 concentration at equilibrium is 0.075 molar. Okay. Now what would be the NO concentration at equilibrium? Let's look over here. NO concentration would be 2 times 0.075. You guys following that, right? NO would be 2 times point because it's 2, because NO is 2x. So that would be 2 times 0.075. It would be 0.15 molar. Okay. And then the last one I need to do, I need to figure out the equilibrium concentration of NO2. Let's come back over here. What would that be at equilibrium? At equilibrium, that is 0.359 minus 2 times 0.075. So it would be 0.359 minus 2 times 0.075. And what I get is 0.209 molar. Okay, so these are equilibrium concentration, right? These are my equilibrium concentration. Concentration, molarity at equilibrium. So far so good? Okay, now what we're going to do. Remember, the main thing was we wanted to figure out K equilibrium, right? The KC is product over reactant. My product would be NO to the power of 2, O2 to the power of 1 over NO2 to the power of 2, right? All I did product over reactant. Concentration of product over concentration of reactant, but the ratios matter. Now, what we're going to do, we're going to plug it in. So NO concentration at equilibrium is, so NO concentration at equilibrium is 0.15. So I'm going to put 0.15. What do I have to do? I have to square it. Now my O2 concentration is 0.075 is to the power of 1 over my NO2 concentration is 0.209, but again to the power of 2. So 0.0209 to the power of 2. What my final answer is going to be is 0.0387 is going to be my Kc. Now, one more time, I know you know this. Again, these are the concentration. I have was in the bracket, but again, you still have to do it to the power of the stoichiometric mole ratio. That hasn't changed. Okay, so we figured out Kc. So far, so good. Now, next one, hopefully getting the next part of this question. Would a system containing 0.45 molar NO2, 1.20 molar NO, and 0.05 molar O2 be at equilibrium? Okay, now you know how to do this. You've done this before. They ask you, are you at equilibrium? Remember that lecture? Every time they ask you, are you at equilibrium? What do you need to figure out? Tell me. Yes, you need to figure out Q. Every time they're asking you, are you at equilibrium? You have to figure out Q, right? And then compare Q to K. So every time they're asking you, are you at equilibrium? You have to figure out Q. And if you remember, Q was exactly the same formula as K. Is concentration of reactant, that would be product, concentration of product over concentration of reactant. Okay, exactly the same as K. Now let's put it in. So right now the concentrations are given to you, right? The concentration are given to you. They tell you that NO concentration is 1.2, so 1.20 times to the power of 2. O2 is 0.05. That's a funky looking 5. Over NO2 is 0.450 to the power of 2. Okay, let me explain this in case I've lost someone, hopefully no one. So every time they ask you, are you at equilibrium, you have to figure out K. K has exactly the same formula as, you have to figure out Q. It has the same formula as K. Is product over reactant. Now, they've given you these concentrations. These are the concentration they have. We want to know if we are at equilibrium. So they're giving you the concentration. They're asking you, are we at equilibrium? I'm going to plug into Q, which is again product over reactant. So they're giving me these concentration. I'm going to plug it in. I still have to do it to the power of a stoichiometric mole ratio. That hasn't changed, right? They just give you what's in the bracket again. So I'm going to plug it in to figure out what my Q is. If I do that, I get 0.356. That is my Q. Okay? So they're giving me the concentration right now. I want to plug it in to figure out Q. You do that every time they ask you, are you at equilibrium? Now, what I'm going to do, I'm going to compare Q to K. What is my K? My K is 0.0387. That is my K. Do you guys agree? So now I can just put K instead of KC. That's my K. C just means concentration, right? So what can you tell me about Q versus K? What can you tell me? Which one is bigger? Q is a lot bigger than K, isn't it? It's 0.3. This is 0.03. So Q is a lot larger than K. Okay, now I need you to think about this. So are we at equilibrium? The question is no. We are not at equilibrium, right? So no, we are not at equilibrium. Let me write it down. So no, not at equilibrium. Now, what do we need to do? In what direction would the reaction mixture need to shift to move towards equilibrium? I need you to think about this. So we figured out Q, we compared it to K. We know that Q is a lot larger than K. So what that means is what? What do we need to do to reach equilibrium? Think about this. What do we need to do to reach equilibrium? You can mute me, pause me, think about this. Okay. Do you remember that Q or K, yes you do, is concentration of product over concentration of reactant. Do you agree? Is concentration of product over concentration of reactant. Okay. Now, if you look over here, Q is too large compared to K. So my Q is too large compared to K. If my Q is too large, that means I have too much of what? That means I have too much of the product. Because it's product over reactant. Too much product, it would be too much Q. Too much reactant would be less Q. So because Q is larger than K, which means I have too much, it's too large, that means I have too much product. Because again, if this goes up, that means I had too much product, and that's what makes the Q to be a large number. So what this means is I have too much product. Okay, so if I have too much product, what needs to happen in order to reach equilibrium? It has to shift towards reactant, right? It has to shift towards reactant to reach equilibrium. And I'm going to explain this too. So we figure out Q, we compare it to K, we're not at equilibrium, is a lot larger than K. So if Q is larger than K, that means I had too much product, right? Because more product means that the Q is going to be larger. Okay, so I have too much product. Now, what do I need to do to reach equilibrium? If you have too much product to balance this out so you can reach the K, that means you have to form more reactant. You have to form more reactant so I get to the K that I want. So it has to shift towards the reactant to reach the equilibrium, because we have too much product, shift to the reactant, so that I would have more reactant, and this would come down and it would match up my K value. Yeah? Okay, this was a good problem. Hopefully you're still following me. Okay, so I think I'm going to stop here. We did half an hour of practice problem. That's good. Go over this problem, make sure you understand them, and then next time there is one more thing about the equilibrium. It's a fun one. We got to go over and then we are done with equilibrium. I will see you guys next time again. Let me know if you have any question about these problems. These are good problems. I will talk to you guys next time.